Hello again, folks, in 114. Today we're going to be covering section 610, which is the last of chapter 6. Let's see, here's the calendar. Today is Thursday, June 3rd, so appropriately section 610. And then we are finished with algebra, at least as a designated chapter. It will always appear in other places, I'm sure. The packet that I have for you consists of this page. This is an overview of functions, which is where we're at now. I'm going to sort of project this in as normal. I'm going to annotate a little bit. Let's see. This is a diagram to summarize how to distinguish something from a function or not a function based upon, well, given that you are a set, an actual drawing, or what they call correspondence figures. You can tell right away in each of those cases. This is a diagram, an overview of the types of functions that you are inclined to see in MAT-114. Right? There's always more to add to this, of course, but this is just what pertains to us. So again, I'll project this and you can annotate if necessary. This is from a different textbook, but it's nice because it essentially summarizes the types of graphs that you would get. And I'll highlight the ones that are relevant to us. Okay. Now, if you're going to graph by hand, this is the process I go through personally when I'm trying to decide how a quadratic function would look. There's steps involved, and little cues, and there are some word problems that we'll go through. Okay, and I think that's it. Right. Okay, so if you're following along, do print that out. To elucidate. Let me turn this on and then I will adjust the lights. Here we are on MAT-114. No, I don't need this. Okay. Let's see. Right. Let's start with this. Okay. In the subject of algebra, you will hear this phrase thrown around: relations. Right. And in a nutshell, a relation can be thought of as a set of any two variables, but typically it's x's and y's. Right. It's not very strict at all. Let me back this off just a wee bit, so I could kind of point to things. Color those things out. Okay. It's not strict. This is more general, whereas functions is more specific. Example of something. Right. Any set of ordered pairs, x's and y's usually. Whereas if you are a function per se, or you have a function, that's a more specific type of relation. Now, how can you tell visually that you're dealing with this and not only this? This is the condition, basically. whereas a relation is any set of x's and y's. Functions per se, they have no repeat x's. Right? So I put no recurring x's to remind you. Right? This is a formal definition that's here, but I've always found that confusing, and it best is summarized, I believe, by that. I'll read it to you nonetheless. For every value of the domain, there is just one value in the range. Well, what is the domain? The domain is the set of x's specifically. Right? The range is the set of y's. Right? Normally, when you talk about a function, if it's a set, right, then it's a set of x's and y's. You know, and then there's the condition that is basically the line equation or what have you, written adjacent. That is after this line that is read as such that. Right. The set is anything in fancy braces of the ordered pairs such that they meet these conditions, and the conditions again are usually presented as a line equation. Right. In the style of a function. A function is I should say a function notation is just a different style of writing it. Right. Now underneath here, there is another even more specific case, which you are not really responsible for. But I don't like to leave things out, and I'm sure that you can handle it as a concept, you know. Right. If the generalization is the term relation, and function is slightly more specific, right, then what would be classified as a one-to-one function is the most specific. Right? Which is why it's at the bottom of this diagram here. Right? I could have written it sort of straight down, but I don't know, it looked more elegant to me this way. One-to-one functions meet the condition of being a function firstly, which means that there are no repeat x's, but simultaneously there are no recurring y's, no repeat y's. Right? It's truly one-to-one. Right? Now, why does anybody care about any of this? A person cares ultimately because these conditions affect the graph. Right? Essentially, these affect the drawings. Okay? Now, there's another thing I fitted into here, right, which I'll emphasize now. There's something called the vertical line test. You see where it says VLT, which sounds like a terrible sandwich, right? Like BLT. If something fails the vertical line test, right, then it is this only. Okay? Whereas something passes the vertical line test, and if you haven't checked anything else, then it is a function. If something passes both a vertical line test and a horizontal line test, then it is a one-to-one function. And again, you care ultimately, especially if you went a trigonometry or pre-calc class, because that affects the drawings, right? If something has to pass the qualification of a function, you might have to manipulate the picture in a very specific way. Right. Anyhow, that's the summary of what these words mean, and you're really just responsible for relations and for functions, because this is the first sort of subcategory of this. Okay, so think about a function as being no recurring x's, and it passes the vertical line test. You'll see what the vertical line test is momentarily. Bear with me. All right. Now underneath here, one thing I want to clarify too before I move on. There's function notation, which might be a little off-putting. All right. People don't realize immediately, this is the case usually, that these are really talking about the same thing. Why? Because there is this unusual sort of notation here. All right. What I want you to accept is basically this. The letter Y and this sequence of what should be an italicized F, parentheses, and then the X embedded inside it. These are interchangeable. So if you feel more comfortable given this, you could write that. All right. Why have this at all? Right? Well, the purpose of this is that this emphasizes that X is the input, which essentially identifies it as the independent variable. Okay? If you had some other, you know how a lot of times when you have an algebraic expression, you might have a slew of different letters, right? So it kind of helps that if you have more than one letter written on this side of the equals, to have the identifier, if you will, the thing that designates that, yeah, that's the thing that you're messing around with. That is the input, all right, or otherwise known as the independent variable. Usually is the case with X, all right? These other parts are basically the same, all right? That's still a slope, that's still a Y-intercept if you happen to have something in a linear equation. That's sufficient, okay. Now, how would you read that? If you were going to read something in this style of writing it, the function notation, the F parentheses X portion of this is read as the function of X, and then equals is, and then you would read the conditions, whatever have you. A slightly more concise way of reading it would be F of X, the function of X, okay? And that's basically all there is to it. Just realize again, you could swap these if you feel more comfortable. In a physics class, a lot of times they don't use the F for the function. What they will use instead is this as an alternative, right? Y parentheses X. I think in that instance it would be just simply for the fact that we're used to Y, right? Again, this is wrapping a parentheses around something is really meant to draw your attention to it. It's emphasizing, okay, that X is the thing that you're tinkering around with. Okay. Now, if you look at this sheet, we'll go through this. This is blank, right? How to tell if you have a function or not, based upon given a set, given a picture, given something called correspondence figures. Another blue. Although this blue actually erases today. So it's cool. Okay, well, as I mentioned earlier, let me see if I can zoom in a little bit on this. It's a wee bit better. A set is a function if, again, just to borrow, no repeat x's, right? So if you were to see something written in the style of the set, and you see some ordered pairs in sequence, I'm not too creative here, but we'll get the gist in a minute. If you see a set given to you, really what you need to look for are the things that are in the X position here, at each of these ordered pairs, all right? As long as they are all unique, right? Another way of saying no repeat X's is all unique X's. Okay. And as you can see, because again, I'm not too clever, I put just three points in sequence here. 0, 1, 2. They're all different, right? They're not repeating. Right? If, on the other hand, you're given a set and an X value occurs more than once, that might look something like this. And then when you zero in on the actual x's, you'll see that they're not all unique. You have two zeros in this case. So this would classify as not a function, but merely a relation. It isn't nothing, it's just this more general thing. Less strict criteria. Okay, what about if you are given an actual drawing? I'm going to draw a very simple graph that is xy here, and then another one over here. Right. We're just familiar with vertical lines really at this point in the conversation, but it'll be more interesting when we get to something else. Let me just simply draw a blue diagonal line on this graph. All right. Something that qualifies as a function does so, right, if it passes the vertical line test. And the vertical line test means no more than one point of intersection per line. What are the lines? The lines are imaginary lines that you use to test, hence vertical line test, that you draw through the graph. All right, now I just drew one imaginary vertical line here. How many points of intersection for that line? Just one. That's good. You should be thorough and test it in several places though, so let's just say that you did it over here as well. How many points of intersection with the blue is the red? In this case, still just one. 1 point. 1 point. All right, and if you kept doing it in the case of a diagonal line, you'd be fine. All right, so this is something that would be considered a function, even as simple as it is, a y equals mx plus b situation, a line, because it passes the vertical line test. If, on the other hand, you had something interesting like this, a sort of sideways parabola, all right? A sideways looking UV hybrid shape, if you will. Right? This is something that you will see that will fail the vertical line test. Right? How come? Because it would be more than one point, more than one intersection per line. Okay? If you have more than one intersection per imaginary line, you fail the vertical line test. So let's start with drawing an imaginary vertical line through here. Right? In this case, it happens to be blue, just for the sake of contrast. How many points of intersection does the blue line make with the red curve? 2, right? 2, right? Without even having to test it in other places, although you should be thorough, right? This is something that fails the vertical line test, right? Because you have more than one point of intersection per imaginary vertical line that you draw. Okay, so not a function, it's just a relation. All right. The last thing, although it's less common these days, I think, is something called correspondence figures. Correspondence figures, to me, they always look like two balloons sitting side by side with numbers written into them and arrows connecting them. So here, to illustrate, say that you had a balloon and you put your x's in here. I'm going to just label them there. 0, 1, 2, and then you have an adjacent balloon here. And inside you see, again, I'm not too creative, 1, 2, 3, and these will be y's. And you see arrows connecting the numbers from the X balloon to the Y balloon like this, to show that there is a relationship. So this is sufficient. Just as before, when you had the set of ordered pairs, 0, 1, this is another way of drawing that. All right, 1, 2, X, Y, and 2, 3, X, Y. If, all right, there is basically only, let me put this in blue, only one arrow originating from each x value. If you have that situation, then you qualify again as a function, right? As you can see, there's only one arrow originating from this x0. There is only one arrow originating from this x1. There is only one arrow originating from this x number 2, right? And these are the x's. The independent variable, or what you might call the input, right? Usually we read these things left to right. Okay. Now, what's the situation that violates that? Here are two balloons of numbers, correspondence figures, and inside here, I'll just put 0 and 2, and then 1, 2, and 3. And these are the x's and these are the y's. Right? If you have this situation, with something akin to it, this is when you have more than one arrow originating from an x value. So for example, again, I'm not too creative, but from this x value that is 0, there are two arrows originating from it. That means that there are recurring x's. If you were to write them in the style of a set of ordered pairs, it would be 0, 1, that's the first arrow, 0, 2 is your second arrow, and then 2, 3 just coincidentally happens to be something else. Okay? So, given a set, given a graph, given correspondence figures, you can pretty much tell visually without doing any calculations whether you have a function or not. Right? Again, a person cares ultimately because whether something is a function or not affects the drawings that are the graphs. Right? In upper level math, what they have to do in certain conditions like this is that they have to eliminate the bottom half of this parabola in order to qualify as a function, to maintain status as a function. This gets erased, right, essentially. Anyway, now let me show you two things. The first one I think is more practical. Again, I stole this from a different textbook. I have to sneeze, forgive me. Somehow I defeated it, I don't know. Should I feel a sneeze coming on and it just suddenly doesn't happen? I'll just just happened to me now. I'm grateful I don't like sneezing. Take a look at this. This is a nice summary of how the graphs of different functions would look. Right, now notice something. They actually wrote them not in the typical function notation. They wrote them in simple y and then what the rule is. All right, incidentally, when you have something written in function notation like this, what is it on the right side of the function notation? This is referred to as the rule. So you might hear that in context sometimes. Now, of these, what are important? You're not really responsible for them. It would be fine to have, certainly this is a reference. Also included is what the domains in theory would be. In other words, what the x's are allowed to be. Domain is essentially the set of x's, but you might think of it as being x's allowed, and range as y's allowed. Okay, in these cases you see that in the case of an ordinary diagonal line, this is the least complex of all line equations. Y just simply equals x, nothing else. The domain is from negative infinity to positive infinity, which means it can be anything. Right? If you see, if you're analyzing this, you notice that they use parentheses in some cases, and then in others they use brackets. That is referring to interval notation, which you're not really responsible for. Right? But and when you remember when we were doing graphing in one dimension, just to make sure that this is clear, we had lines that had dots on them, or lines that had holes to refer to something. And a dot means included, and a hole means not included. It's just a reference. Well, in interval notation, which is what these domains and ranges are written in, it is a very concise way of expressing that idea of inclusion or non-inclusion. Right? So if you see the equivalent of a hole just sort of broken apart, parentheses, all right, that means not included. All right, it's just a reference. If you see something instead of a parentheses, you see brackets, either oriented this way or this way, that means it's included, the actual figure. Like for example here, what is the y value allowed to be? It says 0 is the lower boundary. There's a bracket here rather than a parentheses. It just means that 0 is included. All right. Whereas when you see parentheses, it's not really including it, it's just a vague reference. Right? Infinity is a non-specific place, so you really can't put a bracket. Anyhow, the graphs that would be good to know, right, are graphs that are linear like this. They're calling it identity because it's the most basic type of a linear equation. It doesn't have a lot of meat to it. Right? It's just y equals x as opposed to mx plus b. The slope would be 1, the y-intercept would be 0 in a case like this. All right. The next one that is really relevant to us is this one here, which again is called the square function, because it isn't really including anything interesting beyond the defining feature. You know how we were saying, the royal we, that how do you distinguish one equation from another? By degree. So this is linear and identities, which is a subcategory of linear, would be degree 1, right? Square is degree 2, right? This is where the quadratics, this is how quadratics would look, all right, visually on a graph. There's a name for this. This is known as a parabola, the shape. A parabola is not quite a U and not quite a V. It's kind of the bastard child of the two of them. Because a U would have no point. This definitely has a point, right? They call that a vertex point, at the very bottom of the parabola. And it's not quite a V because a V would have flat sides rather than curves. So it's something in between. If you analyze this a little bit further, you go down the page here, and I'll move it, you'll see that there is in fact a V function, right, which is the absolute value. Right. So a little bit further down here, there's the absolute value function, which is a genuine V. You're not responsible for that either, right? But it exists as a concept. Right? And you can see that this is distinct from the parabola shape because they are genuinely flat sides here. Those have a point too. What is going to be relevant to us, and you'll see later today in this conversation, are what would be classified as the exponential functions. This happens to be a particular type though. All right? They are curves like this, right? Or if they are just tweaked ever so slightly to include a negative, right? What you'll see is that the curve will go downward like this, right? This is known as a decay, whereas this is known as a growth. All right? A growth curve goes through the point 0, 1, or a decay curve which goes through the same point. The figure that you see here is a little teeny tiny e. That is one of the sacred numbers in math world, right? But in theory, it could be some other base. It doesn't have to be that in order to qualify as an exponential function. All right? So know those three types, basically: the linear type, the square or quadratic type, and the exponential type. Right? I have another diagram to summarize that, but this is how the graphs actually look. Right, diagonal lines, parabola shapes, growth or decay curves. Okay. Now to summarize that, take a look at this sheet. Sorry, I pulled the curtain here. I may, well, you know, it's fun actually. Let me show you this. This is cute, I thought. It's a funny way to remember how the graphs look without using an actual coordinate plane. And there's something of a stick figure here. Simple drawing where a person is simulating what the shape looks like with their arms. These are trig functions, which again you're not really responsible for, but you could see again, here's the V shape for the absolute value. Here's the diagonal line for just standard x. Here's the parabola shape for x squared. A circle would be x squared plus r squared, pardon me, x squared plus y squared. And then there are these other ones. Reciprocals curve like this. That's 1 where x is a denominator. Here's an interesting example. The square root of x. This is one of those things that in order to qualify as a function, all right, when you see the graph, it's sort of a sideways parabola, but they do not include the bottom of the parabola because then it would not be classified as a function. So that gets deleted. All right. All right. Now let me show you this. This is an overview of what you all will see, all right, in the forthcoming conversation for this class. Okay, types of functions. All right, essentially what I've been saying: linear type. This is not graphical. This is just algebraic notations. All right, quadratic type and the exponential type. All right. Again, I tried to make it easy to distinguish one from the other. Train your eye to look for the degree. All right. Linear type or degree 1, the quadratic type or degree 2. All right. The exponential type is interesting because the actual variable becomes an exponent. That's the input. And instead, the base number can be whatever you want, but it is consistently the same once you choose it, right? So this could be anything also. Well, almost anything. But it is consistently the same thing once it's decided. The base, I should have put this as an A here, I neglected to do that. I put N, right? Is anything that is greater than 0 with the exception of 1 itself. Right? Why? Because if you had 1 as a base, it would just consistently be 1 no matter what the exponent is. Here's proof of that. If you took your calculator and you put 1, raise it to an exponent, see what you get. All right. Even if you use 0.2, you get 1. If you use, 1 to the 1, you get 1. If you use 1 to the 2, you get 1 consistently. Even if you put 0 in, all right? 1 to the 0 is still 1. Sorry for the glare. So it would be pointless to have that, right, which is why it doesn't get used. All right. Other than that, it's something positive. It could be any decimal between 0 and 1, right, as a base. But more likely, you start at 2 usually, or you have some specific thing like base E. Right. Now, as I mentioned, E is one of those sacred numbers. It's Euler's number specifically. It originates from finance rather than geometry, as in the case of pi. Pi is another sacred number, right? 3.14159, whatever it is, into infinity. These are examples of irrational numbers, right? They're infinitely stretching and they have no perceptible pattern. Anyhow, they're very good to know, right, what the approximate is. So E is 2.71, 2.72 if you're rounding to the hundredths place. And it is in the same category as pi. Now imagine you had that as the base specifically. It's very useful for something like growth or decay, in science, for example. Now, when it comes to the quadratics, which you're really more responsible for, all right, there are different forms that it will be given to you. All right. What's annoying to me personally is the switching of the names. All right, we're talking about functions, which are granted types of equations, but when you're speaking about quadratics as the function, this is the word general form when you're referring to something that looks like this. All right, if instead you might have noticed when you're talking about equations that look like this, they don't use the word general. They use the word standard. But in function world, this is the standard form, which is why there is alternatively another name for standard form of a quadratic function. Just so that there isn't confusion for the switching of the names, what they will say is that, oh, well, this is vertex form, which I think is better. So vertex form, all right, looks something like this, all right? There is a third sort of shape, if you will, model that you might see, although you're more inclined to say pre-calc or something like that, which is the intercept form, right? Now, how would one distinguish general from vertex or intercept? The general form is not factored at all right? The standard form is kind of partially factored, all right? For the purpose of revealing the vertex, the number that is sitting here and here, which is weirdly designated H and K, that is the vertex. It's the very bottom of the parabola shape. So as you noticed in that other sheet, the parabola shape is something that essentially looks like this. the very bottom of it is referred to as a vertex. It's a point, right? And when you're trying to graph something, especially by hand, it would be good to have that as one of the points that you use to draw. Anyhow, do be careful of something. The h value is counterintuitive. So even though it looks just fine as being h and k, if it appears to be a negative here, then that means that it's a positive here, right? For the h, right? If it appears to be a positive here, it is a negative there. Okay, that's a little annoying. Thankfully, the k is consistently whatever it is. So if you see positive, assume positive. But the h is counterintuitive. It's always opposite. All right. Now the intercept form, which again you're not going to see this, but how to distinguish it from the other categories? The intercept form is, this is a typo. This is completely, I have to fix this now, completely factored. I wrote this yesterday, so I have to fix it now. Sorry. The intercept form is completely factored. The standard vertex form is partially factored, and the general form is not factored at all. All right. Now, why would you completely factor something? In the case of the intercept form, do so to reveal something that is referred to as the zeros. The zeros are the value that is, hard to see because I drew on it here. The number that is sitting here in the parentheses and the number that is sitting here in the parentheses. They're called P and Q a lot of times. Anyhow, they are the X-Intercepts. Zeros is a fancy way of saying X-Intercepts, right? And you're really just paying attention to the P value and the Q value to place a dot when you try to graph by hand, right? Now here's a side note too. The Y-intercept, which we're usually more interested in than X-intercepts for diagonal lines, and the vertex are, not all of the time, but sometimes they're the exact same location, right? And you know how to get Y-intercepts, right? You put a 0 in place of the X, and then you simplify, right? And that will reveal that. Similarly, if you're looking for the X-intercepts, you put 0 in place of Y, and then try to solve for that. Okay, so just to reiterate here, linear produces diagonal, sometimes horizontal lines. Quadratics produce this parabola shape, which is kind of a V, kind of a U hybrid. Exponentials produce the curve that is either growth or decay, which you saw a little bit earlier. Looks something like this. If it's a growth, from left to right, it points up like that. If it's a decay, it goes through the same point. From left to right, it goes down like this. Okay? And there's an option. You could change this base number to something that would be like 2 usually, or another number that's not 1, and it's greater than 0. All right? Or, and this is very interesting, to have E in place of that. Right? As I mentioned, E is a sacred number. All right? It comes from finance rather than geometry. This is useful in describing something like population growth or bacterial growth or radioactive decay. Of a substance. Yeah. It helps basically predict natural phenomena. Okay, so it helps. That helps. Just beware of that typo there. That should say completely, not partially, because as you can see, that's completely factored. Whereas this is partially factored. Not at all, partly, completely factored. Okay. Let's see. Let's do a word problem. And then we'll sort of switch back and forth. The first word problem is to get your feet wet in terms of dealing with function notation, just getting used to reading it. So what you see up in purple here we'll deal with first. Celia's weekly salary as a real estate agent, S, this is getting to be a dud, is given by the function S of X, right? Whereas we used to seeing Y, and then we swap that out with function of X. In this particular problem, they've adapted the function notation to represent S for salary. And it is S of X is equal to 100 plus 0.03x. Now, if you wanted to sort of conform this to the usual mx plus b shape, the figure, the term that involves the actual exponent, pardon me, the actual input x, would be immediately after this. It doesn't have to be that way. But if it makes a person more comfortable, I would take a little artistic license, rearrange these. They're commutative, you can do that. All right, plus 100. Right. Where X is the weekly sales in dollars. What is Celia's weekly salary if she sells one house for $85,000 in a week? All right, so sales is representing X, and in this particular case, 85,000 is going to be the input. Right. That means that you're just going to insert in place of X the input of the situation, which is $85,000. Now I want you to notice some things. In traditional y equals mx plus b, b, the y-intercept, is essentially the starting point, right, when you're graphing in real life scenarios. Because it's 0 and then whatever this number is for a coordinate. Right? And this term here is the slope attached to x, right? And that basically converts the bottom unit, whatever the bottom unit is, into the top unit. So what does that mean? Well, this whole thing is rigged to basically express a quantity of money. Right. So 0.03 is actually literally 3 cents, but it's $0.03, right? Since we're using $85,000 here. Right. Okay. So really it's just a matter of following the order of operations because you were just sticking with this one side, the rule of the function. So put 85,000 where it appropriately should be, multiply by 3 cents first, or 3/100ths of a dollar, and then add 100, right? Which means that when all is said and done, you should get this, 2550 plus 100, which should be 2650. This is what Celia's salary would be. Essentially working, which sounds like commission. Just to verify, 0.03 times 85,000 plus 100. is indeed $26.50. So $2,650, not bad, right? Okay. I wonder if it's appropriate to do the next one first. As an American, and it's nearing that time of year, I think I'll do the green one now because it is an interesting usage of function notation. Right. On July 20th, 1969, the Eagle spacecraft landed on the moon. Right. The velocity of which in meters per second was a function of time. Right. Consider what's happening in this case. The function notation is, again, it's being adapted to the problem. So, whereas we're used to saying y equals something, we're using function notation, but the function notation is written as f of t. Right? It's just emphasizing that time is the variable input, right? And it's really standing in place of what would be a velocity. This whole thing is represents velocity. So it's written in basically mx plus b form. It's just that this is a 3.2 for the slope, or the rate of change in this instance. And this is t is being replacing x. So you have 3.2 with a t attached to it plus 0.45. Okay. Again, the whole purpose of this is just to get your feet wet so that you're comfortable with reading something in function notation and just realizing that they've changed the labels. That's it. Yeah. Okay. The velocity of the Eagle spacecraft is calculated in meters per second, otherwise known as the velocity, right, was a function of time and could be described by this function, 3.2t plus 0.45. The height of the spacecraft above the moon's surface, h, right, was also a function of time, and it could be described by this other function, right, which, to distinguish one function from another, often what will happen is, if f is the starting letter, then what we will do is we will use the next letter in the alphabet. The English alphabet is G. Right, so this is standing in place of height, right? Versus this is velocity. And again, they're both adapted from traditional function notation, which itself is adapted from y equals mx plus b. A rate plus a constant. Okay, find the velocity and height at 3 seconds before touchdown and at 0 seconds, i.e. at actual touchdown that they've made a connection with the surface of the moon. So you're basically going to do 4 calculations when you're doing this. All right. It's not too complicated, but I don't want to move the slide, so let me try to reserve some space here. All right. This will be for 3 seconds before, and this will be for 0 seconds before, which is not really appropriate to use the word before, perhaps. Okay, so if we calculate the function at 3 seconds, a lot of times the way that we will write that, instead of putting the t here again, when we're evaluating the function, we put the 3 in place of the t to show that that is being used as the input. So then you have basically 3.2 times 3 plus 0.45. And then simultaneously, the height at 3 seconds to evaluate is 1.6 times 3 squared plus 0.45 times 3. This is a little bit more complicated. Velocity is derivative of height, position. Okay. Over here, just to get the machine going here, you'll have 3.2 times 0 plus 0.45, and for G, height again, 1.6 times 0 squared plus 0.45 times 0. This one, if you do that one first, you might laugh a little bit because you'll see what the result will be immediately. And that makes perfect sense because we're talking about a position here relative to the surface of the moon. You know, it's a height above the moon. Well, if you use 0 for at the amount of time that is right at touchdown, and you put 0 here in the function and here in the function respectively, 0 squared is 0, 0 times 1.6 is 0, 0.45 times 0 is 0. So, as to be expected, this is a height equal to 0 meters, you know. How about the velocity? All right, the velocity, interestingly, the way that it's calculated is it's at the 0 second. The first term here will cancel, right? But you would technically be left with some kind of velocity as part of this calculation. So the velocity in this instance, somewhat counterintuitively, is equal to 0.45 meters per second, which basically implies that there is a force, right, occurring here. You're going to be coming to a dead stop in the span of 0 seconds. All right, from that. All right. Which is why there's probably an impact, you know, a dent in the surface. Now, if you do these, remember, follow the order of operations since you're dealing with the right side, the rule portion of the function. So you don't have to deal with the left side really at all when you have something in function notation. That's kind of a nice thing about it too. But you do have to follow the order of operations. So what you would end up with is essentially 9 times, because it's 3 squared first, 1.6, multiply 0.45 times 3, and then add these. And in this instance, the height would be what? What you should get is 15.75 meters, since that's the unit. Okay, similarly, if you follow the order of operations as you should here, 3 times 3.2 you would do first naturally because it's of higher order, and then you would add 0.45. So the velocity in this instance is equal to what? It should be 10.05 meters per second. Again, the purpose of this is just to get you used to function notation and tinkering with it, putting the numbers in the appropriate places in whatever incarnation of a function they give you. Right? They just change the labels, right, to adapt to whatever the problem is. So I'm just 1.6 times 9. It's always good to check. Good. All right, that's all legit. Okay. So 3 seconds. Velocity 10.05. Height is 15.75 meters. Okay, right at touchdown, there is a velocity technically, and the height is, naturally 0. Okay. This, which is following carbon dating, I'm going to come back to because we have to get through graphing first. So let me pull up this slide now. Key features of a quadratic function. And we'll practice a graph. Now, depending upon which incarnation of the quadratic function, that is what, whether it's in general or standard primarily, you will use one formula or another to glean the appropriate information, like a vertex location and so forth. Let's start with this. If we're talking about a quadratic, then it produces a parabola. And again, a parabola is this shape. It's something that is, in its most basic form, goes right to the origin, the most basic type, and 1, 1, and negative 1, 0, negative 1, 1. It's sort of a hybrid VU shape. Right? It's curved, so it's not quite a V. It has a point, so it's not quite a U. So think of it as, again, it's illegitimate child, like me. So anyhow, now what you can tell if you're just staring at the, never mind the graph, but if you're staring at the function, the algebraic symbols, you could tell whether it opens up in this orientation or if it sort of points downward in this orientation by the value of the lead coefficient. So remember, even if you have something given to you in the general style, versus something given to you in the vertex or standard style, train your eye to look at the A value. What would be sitting in the position here or in the position here? Right? Because that immediately, just whether or not it is positive or whether it is negative, will decide whether the parabola is oriented like that or potentially oriented like that, upside down, just based upon having a negative or a positive up in the front. Okay, so I think of it again, if you want to call a parabola, instead of saying hybrid UV shape, call it a tulip, right? It either opens up like a flower blooming or it wilts, all right? So it's drooping. Now, as for the how wide the parabola is, that depends on what type of number you have here or here. If this is essentially, somewhat counterintuitively, a fraction, all right, you could expect it somewhat ironically to be wider than normal. So you would have a parabola that looks like this. It's like the bloomin' onion now. Wanza! Yeah, that's kind of cool. If you had something that was a number that's greater than 1, right, to generalize here, it somewhat ironically, so something like 1.5 or 1.5, etc. it actually makes it narrower. So you'd have something that's a little bit more like this. Right. This is again, not to be blasphemous, but if you want to, if you're graphing something, pretend for a while that you're a math god, you know, and just by manipulating a number or a sign, you could change the picture, right? You could create something. It's actually a very kind of an empowering feeling, right? When you're trying to flesh out the drawing, though, right, aside from how the basic shape would look, wider or narrower, there are some points that you want to get every time, and the first one is the vertex. And they're not difficult, all right? If you're given something in, again, the standard form, which looks like this, otherwise known as the vertex form, if it's already arranged this way, just look for the number that is here and here, right? And make that the ordered pair. And then there's a dot that you have to help flesh out your picture. We're going to do an example in a minute. Just realize, again, the h value is counterintuitive. All right, if you see a minus here, make that a plus, all right, and vice versa. When you're given the general form, there's a formula that you would employ, all right? It's just this. The x portion of the vertex coordinate, remember the vertex is an ordered pair, x comma y, so it's a dot. Use this. The value that is sitting in the b position of the general form, negative, over 2 times the value sitting in the a position. Right. That will give you the x. There is actually a formula specifically for calculating the y, but it's more trouble than it's worth. So what would be practical really is to calculate this and then use that value as the input in the function. Because remember, if f of x is standing in place of y, then if you evaluate the function, using the x number that you just calculated, that will tell you the y that ought to be. Okay? So you decide to use that formula if you have general. You just basically take this information if it is already partially factored. There's this concept in Axis of Symmetry. Once you have the actual vertex coordinate, and again, you're doing this by hand, draw an imaginary dashed line similar to this right through the point, right? Vertically. That is a perfectly vertical dashed line. It's just an imaginary line, all right? That will help you predict other points without having to do a calculation per se. You could if this is superimposed on graph paper, you can basically count some boxes to help flesh out the drawing, because there is symmetry, right? That is, the picture looks like the mirror image on opposite sides of this line. Okay, then there's these old reliables here. The X-Intercepts. How do you calculate an X-Intercept? You stick 0 in place of y and it's simplified, right? How do you calculate a Y-Intercept? A lot of times it is in fact the vertex point, but just to verify it, you put a 0 in place of x, right? And as long as you have those 3 points, you have a very good graph, right? So we'll do an example of that to calculate, to illustrate. Okay, we'll do the harder one. All right. I'm going to put this graph paper over here and maybe do the calculations adjacent. Maybe a little water because I'm thirsty. as an example, let me get rid of that. We're going to graph this quadratic equation. So we're going to have y equals x squared minus 6x plus 8. Okay. Now, again, let us decide. Is this the general form of a quadratic function, or, and I have to emphasize function because, you know, the switching of the labels between functions and equations, or is this in standard form? It's the general form. So we need to pay attention to what is sitting in the A position, the B position, and the C position ultimately. Okay. What do you assume is the number that is sitting up in the front if it's not written? Right, the coefficient would have to be a positive 1 if it's not written there. Right? A couple of things that we can tell immediately from that. Right? I'll put a bullet point here. Since A is exactly equal to positive 1, that means two things. Number one, it opens up. And number two, it is the normal, shall we say, width of the balloon. Okay? We already know that since this is squared, that this is going to be a parabola. Okay. Next thing, let us calculate a vertex. All right. Since we have the general form here, we have to employ that other formula, that x is equal to negative b over 2a. And then we're going to evaluate the function using this to figure out what y is. These are the vertex point. Okay, so if we do that, the value of b is a negative in this case. It's a negative 6. So we would put a negative 6 in here. Do be careful, there's a negative in the formula. And there is a 1 here for the a, so it's really times 2. Alright, that makes this positive 6 for the double negative over 2, which is a positive 3. Alright, x is equal to positive 3. If we now take the function itself and evaluate it at 3, that means that we would put the 3 here. And the 3 here. We could spit out what the y value would be. All right. Follow the order of operations, that is, just stick with the right side, the rule, quote unquote. We do the exponent first, which would be 9. Then we do the regular multiplication, which would be negative 18. And then we have our choice between subtraction and regular addition. They're equally important, so we do what is on the left. In this case, it happens to be subtraction. That means that this is negative 9. All right. 9, positive 9, minus 18 is negative 9. Now, one of each sign left over, we actually subtract, which means that we're going to produce a digit of 1, and we will take the sign of the larger magnitude, which in this case happens to be negative, so it's negative 1. All right. So this is negative 1. If you write them in the style of a coordinate, that is ordered pairs, I should say, x comma y, it would be positive 3 and negative 1. Right? We could, if we want to, immediately put a dot to satisfy that. So let's do that. All right? From the origin, count over 3. 1, 2, 3. Down 1, you have a dot here. All right. Now the next thing is that we have the axis of symmetry. That would be a dashed line that goes through this. In that event, I'm going to draw with a ruler a dashed line right along the grid line here. Again, the point of this is that if you have an axis of symmetry, parabolas are symmetrical, at least horizontally. You could use it to predict more points to draw a better picture without having to actually do a calculation. So it's a kind of a cheat, but a legal cheat. If you want to, you could label this Axis of Symmetry. Think of it as being something like a mirror. All right. Two-dimensional mirror as opposed to three. Okay. Next thing, let us get some the X-Intercepts. Right. The X-Intercepts, I may need the space, so what I'm going to do is I'm going to take the original equation and maybe do some work over here just not to affect the picture too badly. I'm just drawing over here. So if we had y is equal to x squared minus 6x plus 8, and we're looking for x-intercepts, otherwise known as zeros, we're going to stick 0 in place of y and then see what we get. All right. Now, if I put 0 in place of y, right, that leaves me with something you may remember from section 6.9, which is that I have a quadratic equation set equal to 0. I could attempt to factor this and then use the zero product rule. X squared minus 6x plus 8 would factor like so. As an x in the front and an x in the front. If you consider the factors that make 8, it would be either 1 and 8 or 2 and 4. Of those two choices, 2 and 4 would make 6. If they add. Now, same signs causes adding to make something bigger, but they have to both be negatives in order to accomplish a negative in the middle. Okay. Then you would go about the process of employing the zero product rule, which is to say, all right, well, maybe x minus 2 is equal to 0, this chunk, this factor, or maybe x minus 4 is equal to 0. Right? And in that event, you're just going to solve two teeny tiny little one-step equations. Right? If I want to move negative 2 from here over equals and negative 4 over here over equals, I'm adding 2 and adding 4, and I get, in this case, the x value is equal to 2 and the x value is equal to 4. Right? But in this style of coordinates, so for the x-intercept, having substituted 0 for y, that means I have 2, comma 0, and I have 4, comma 0. So now what I'm going to do is I'm going to add that to my picture as it's slowly coming into resolution here. 2, comma 0 would be from the origin 1, 2, and then just stay put because it's 0, and then back at the origin 1, 2, 3, 4, and then stay put. Right. So you can see, although it's not very good, it's not fleshed out enough, I'm getting a slowly fleshed out picture of the parabola shape. Okay. So, in order to make this more satisfying, all right, what I'm going to do is I'm going to calculate the y-intercept, and then I'm going to take advantage of the axis of symmetry. So, the y-intercept, since I'm running out of space now, don't go to sleep. The y-intercept is also easy, right? You're just going to put 0 in place of x instead. So that's going to make this really easy, right? Watch what happens. If it is, again, x squared minus 6x plus 8. And to solve for y, I put a 0 in place of x here, and a 0 in place of x here. This term and this term are immediately eliminated, right? Which means that y is just equal to 8. Right? Now, in the style of coordinates that is an ordered pair, it is 0 for the x input, and then a 8 for the y value that it spits out. That means that with more certitude, I could now put a dot along the y-axis at the y-intercept. Right, so from the origin, 0 is neither left nor right, right? Correct. So I'll then go up 8. 1, 2, 3, 4, 5, 6, 7, 8. Put a dot here. And then my picture, rather than being willy-nilly like that, is more appropriately like this. Right? It's a narrow, well, it's really normal, is the way it really looks. A narrow parabola. It's really of the because it's a positive 1 for the coefficient of x squared, it really is the way it should look. Right? So it's not really narrower, right, or wider. Right? Now, again, here's where the axis of symmetry would come in handy if you're doing this by hand. Right? You have a good amount of points here. You have what you absolutely must have, which is the vertex, and you know the appropriate orientation. But we can take advantage of the axis of symmetry to get one more point. Right? As long as this is on graph paper, and we are thankfully on some nice, right on some grid lines where they cross. Right? How many boxes wide is it from here to here? It's just 3 boxes, right? So one would have to assume, since this is symmetrical, as if this was a mirror, that it would be the same distance this way, right? To and from the axis of symmetry. So we can imagine a point here without actually having to calculate it. You could, if you wanted to, just kind of, if you wanted to prove or not, go over to 1, 2, 3, 4, 5, 6 for the x value, put 6 here, here, and then run the numbers, and you will get what should be this point. I'll do that as an afterthought. But what you can do now is, rather than have this willy-nilly picture, draw the rest of the parabola, and you have a nice fleshed out drawing. So, something that looks like this. That's a bit terrible. Why green? Why? How do you suck so bad? That's a little bit better. All right. This is using axis of symmetry to help. Right? If it is the parabola is 3 spaces away here, then parallel, well, right across from it on the opposite side, it would be the same 3 spaces to be symmetrical. All right, again, just to prove that that is true, I'm going to go to just underneath this point along the x-axis and prove that that should in fact be 8. 1, 2, 3, 4, 5, 6. So, if I took the formula, let's see, I'll put it in blue again. Y equals x squared minus 6x plus 8. And I inserted 6 in place of this x here and here, and then follow the order of operations of the rule. 6 squared is 36. This would be minus another 36. 36 minus itself is just 0. 0 plus 8, y would be equal to 8. Right there. Okay, that's pretty cool, right? Again, pretend that you're a math god, all right, and you're crafting. Only you're limited to as a math god. You're limited to working in 2 dimensions rather than 4 dimensions or more. You know. Okay. Now, let me get back into the exponents now, exponential equations, to show you this. I already talked about it, but it's better to re-emphasize now. Okay, let's look at this side of the graph here. I'll zoom in just a wee bit. All right, we're going to get a slightly different picture. Again, the exponential functions will produce a growth or decay curve, which again looks something like this. If it is a growth, it'll look something like that, reading it left to right. If it's a decay, then it will go through the same point, but pointing down. This is useful, again, trying to describe natural phenomena like population growth. Right? If you're given an equation, something like this or this, right, just to dissect it, right, this is the basic idea. You know, there's a number and then the input variable is the exponent. If you decide upon a base being a, as in any number, not 0 or 1, or you decide upon the base being e, then at that point you could amp it up. You could make it a little bit more sophisticated than just that, right? Remember, we have a very simple version of the line equation, y equals x, right? A very simple version of the exponential function would be y equals n to an x. All right. These other features make the picture just a little. It's still that basic shape. It's just that it's going to be applied to some specific problem. When you see a subscript with a little o, which is read as naught, right? P naught, say for example, is the original amount of something. Why the letter P, for example? Because this usually pertains to something like population. You know, an amount of people. It doesn't have to be, or an amount of bacteria either. It doesn't have to be P, it could be some of the label, but let's stick with P for population. A is the actual base here. So in my model, it would be an N, but so be it. This, if you wanted to, again, fine-tune that basic idea to some unique problem, there'll often be a constant that is unique to the problem. So K is in constant. That's very German, I want to say. Why they use K rather than something else. See? The actual variable, as you can see from the function notation though, what would normally be X is T, because that stands for time. Right? Usually it has to be time in years. Right? If you had this incarnation of an exponential function, the only real alteration is that the base would be specified as being e, which is again Euler's number. Right? To give you some satisfaction, it's approximately 2.7 something. All right, like pi is approximately 3.14. They're both special. All right, they're irrational numbers, and you want to keep them. They're sacred. All right, but pi originates from geometry, whereas Euler's number comes from finance. Okay, just so happens to be practical to describing radioactive decay, you know, or a population growth of some sort, you know, perhaps. All right, now, having said that, maybe just point out one other thing. Usually when you see a graph like this point that I keep drawing here on the simple diagram, get this a little bit out of the way to make it easier to see. That point is usually, to start with, 0, 1. Then, if there is another point, if you had to do this by hand, it would be the number 1 and then whatever the base happens to be, right? Depending upon what base you have, this might be a little bit steeper, a little bit more shallow. But as you analyze those, all of these different types of functions, you'll notice there's consistency in those points. Right? They're not specified, unfortunately, here. But if you connected the line, this diagonal line, for example, from the axes to the actual function, you'd see that it's 1, 1. All right. Similarly, in the square function, it's 1, 1, and 0, 0, and 0, 0, 0, 0, 1, 1, and so forth. All right. The exponentials would be like that too. All right. In this case, it starts back and goes through the y-axis at 0, 1. All right. Eventually, you could connect to it. All right. This is a little bit sharper an example when you have e. All right. Because the number is 2.7, so it's hard to see perhaps, but if you have a base e, as in this example, the actual x-axis would connect here at about e for the base, 2.7. Okay. All right, let's go back to a word problem to get your feet wet on this. I'm almost finished. Okay, now interestingly, here is a version of an exponential equation. Don't be intimidated by it because it's written sideways. It's still this idea that the input is an exponent rather than on the usual tier. All right, carbon dating is actually fascinating. Right. Carbon dating is used by scientists to estimate the age of fossils, as you probably know. One incarnation, this is probably several, of the dating formula is this, right? Sticking with P, but T for the input as time, all right? Is an original amount, base of 2, and then notice that there's a negative here, which means that there's a decay, all right? Time divided by 5,600 years, which I'm going to go ahead and guess this 5,600, which is unique to the problem, is more or less the constant k, right? But it happens to be a fraction, all right? This is probably the half-life, right? Half-life is the amount of time it takes for a substance to reduce by half radioactively, right? Anyhow, if you read further, P naught represents an original amount of carbon 14. Carbon 14 is radioactive carbon, right? And not to scare you, but basically everything natural is naturally radioactive, minutely, right? It's not life-threateningly radioactive like plutonium. I don't know why I'm laughing at that. It's not really funny. A naturally radioactive form of carbon that gets replenished while an organism is alive. Right? This is really genius, whoever decided that this would be an appropriate way to date something. As long as an organism is alive and everything is naturally radioactive, it's going to naturally ingest air, food, and water. And in the process, it will replenish its radioactive carbon. Right? When it dies, dead people don't eat, right? So it ceases to have a replenished amount of carbon-14. And what then therefore happens is that over the course of many, many years, the carbon-14 depletes, right? So there's less and less of it. So based upon the half-life of carbon-14, which apparently is 5,660 years, something like that. 5,600 years, sorry. They can compare, how much time has transpired, right, from what should be to what is. All right, so the function P of t represents the amount of carbon-14 present at the time of analysis, that is presumably the present, right? T years since the organism died, presumably, right? If 10 milligrams of carbon-14 is present in a recently discovered bone, right? This is the number that you need really. How many milligrams will be present in 3,000 years? All right, now, the numbers that we're going to use are 10 and 3,000. And let me make a little bit of space. I'm going to scoot this up so I have more places to write. And I'm going to write the formula that we are given next to it. So we have adapted our usual y equals something to function notation, and unique to the problem, we've gone and changed the labels to p of t instead of f of x. Right? And we've tweaked the exponential function to be a little bit more sophisticated, to conform to these circumstances. So what we have is this. We have p naught times, I'm going to put a dot to really show you that there's parts here that are distinct, 2, and then there's a negative up here, t, over 5,600. Okay? So, P naught is the original amount of the substance. It's 10 milligrams. So in here, we're just going to substitute the number 10 for right now. What we will get is, how much time has transpired. In place of t up here, we're going to substitute 3,000. Okay. So we have essentially, if we're paying attention again to the right side of the function, which is really all that we should pay attention to. This is again the rule of the function. We really just have to straighten this out according to the order of operations. We have regular ordinary multiplication here. And then we have the exponent here applied to 2. But this is interesting because there is a negative here, which means that there'll be decay. The amount of the substance will deplete. And we have this ratio of 3,000 years to presumably 5,600 years. Right, so we have to simplify that. Right? What you're going to do probably in a situation like this is try to avoid round-off error. So if you're going to enter this into your calculator, and I would, right, be very super careful about how you do that. Right? Use lots of parentheses to make sure that it's crystal clear to your machine, all right, what has to get done. The calculators do not really reliably know the order of operations, which is why they sometimes give you an erroneous figure. All right. Okay, so let us start with this. All right, just for the, I'll put the 10 as an afterthought, all right, if necessary. Or if you're going to put it up in front, use the parentheses. All right, so you're going to put 10 times 2. And then remember, if you want to get an exponent, right, use the upward pointing arrow here, the caret symbol. Again, encapsulate it in parentheses. Right. And then you could put negative 3,000. Just associate the negative with this figure 3,000 because it has to go to one or the other, not both. So negative 3,000 divided by 5,600, and then close the parentheses. And it should be good to go. All right. Let's see what you get. Sorry for the glare. 6.8. That looks correct. Good. Now think about this. Right. At the time of death, presumably, of this fossil, there was 10 milligrams of carbon-14. Radioactive carbon. Because it's radioactive carbon, what ends up happening is I believe it turns into nitrogen in the process. Right? Over time, radioactive decay occurs. Nitrogen. One substance turns into another, believe it or not. And what you're left with is there are approximately, if you're going to round it to the 10th place, there is about 6.9 milligrams left of C14, radioactive carbon, right? Where did the balance of 3.1 approximately milligrams go? It turned into nitrogen, all right, which is a gas, which means it probably escaped, all right, from the solid, all right. It's interesting, actually, the subject of radioactivity. Anyhow, it's not life-threatening radioactivity, it's just a natural process, so don't get scared. Even it's just a word problem, right? All right. Isn't that cool, though? This basically calculates the amount of a substance after an amount of time has transpired, right? The function is, it doesn't say that in an obvious way, the way that it's abbreviated, but that's essentially what it calculates, 6.9. The amount of substance left after an amount of time. All right, just try to avoid the, don't round intermittently because you'll get a less reliable figure. Let's see. Let's do one of these as a graphing problem, perhaps. Let's see. Look at this one that follows. And I think this will be the last thing. This will involve E as opposed to 2 for the base. The world population in 2012 was a little more than 7 billion people. Assuming that the world population will continue to grow exponentially at a growth rate of 1.2%, right, per year, the expected world population in billions of people, so many years after 2012, could be calculated by this formula. I'm going to write that up here. So, population, this is an appropriate usage of the letter P, right? Population as a function of time since 2012 is equal, is another way, very verbose, right? But that helps illustrate. It's time, but it's time since 2012, right? It is calculated by 7.046 billion people without having to write the extra zeros, right, times the base of E to the constant 0.012, that's the percentage, 1.2% written in the style of a decimal. Remember, is scooted over 0.012 here in a usable form, times the amount of actual years, T. Okay. Remember, this is an exponent, so it's a little bit higher up. Okay. And this is, again, 1.2% growth rate times time in since 2012. Okay, you have here the original amount of people in this case. All right, and you're going to multiply that by an exponential growth. This is times exponential growth. Presumably, you know, it's a model, it doesn't necessarily have to be true. And that will tell us the population eventually, right? However long we want. It's for the sake of predicting. Determine the expected world population in 2018. Okay, so we'll do this here. If, to borrow this, we evaluate the function as years since 2012, right? What is actually the difference between 2012 and 2018? Because that's the figure, that's the actual number we're going to use. All right, it's just 6 years. So you're going to evaluate the function at 6. That means you're going to take 7.046 multiplied by e to 0.012 times, again, inputting here the 6 here. And this will give us what we expect would be the case, barring COVID or some other horrible catastrophe. All right. So again, be very careful. You're just paying attention to the rule side of a function. So you're just tinkering around with this, but you do have to follow the order of operations correctly. And since you would probably be using your calculator, just make sure that the calculator understands, the order of operations, because they don't. All right. They may do some things intuitively, but not enough. They're a machine. All right. So 7.046 times. If you want to get e on this calculator, you have to hit the second function. So you notice that over here we see ln for natural log. You would have to. It's in a slightly lighter color blue. In order to engage that, you would need to hit second first and then press this button, and now you have base e. You can get away once you have that. It automatically puts the parentheses and putting the decimal 0.012 for the percentage growth rate times 6. And this is going to be a growth rather than a decay because there's a positive there. So here we have this. Okay. It should be good to go. The machine is set. Hit equals. And this is billions of people. 7.27. Or 7.57, sorry, I'm reading it backwards. Okay, so this predicts that it's going to be about 7.57 billion people. Naturally, it increased. It increased from what it was, just over 7 billion, to almost a little more than 7.5, according to the model. I Googled this, and according to Google, Google said it was actually 7.59 billion people, actually. Right? Which you can see is pretty close. Right? Now, this is a mathematical model. Right? Why is it that it didn't produce exactly what at least Google has specified as the population? Because there are unforeseen factors, terrible earthquakes, volcanic, explosions, war, things that are beyond the scope of the formula here, right? But it's still pretty good, all right? That's a very reliable model for predicting the future. That's what math is about, believe it or not. It's predicting the future. Okay. And that's about it, I want to say. Let me just check one more thing real quick. If, if you want to explore this a little bit more, right? You're not responsible for it. But if you want to explore how this curve develops, population growth curve or radioactive decay curve, to get your feet wet, maybe graph something like this. This is not, again, something you're really responsible for, but I want you to really feel a firm grasp of something. All right, start with the most basic function you could possibly think of, y equals, let's just say, a half is the base, because that's legally allowed. It's not 1, all right? And then you have an x here. And then build a table. Earlier in this chapter, I had given you something as inputs. and you use that to determine outputs. And then if you have that in tandem, you have yourself some coordinates, x and y. Now, what would you use as an input and an output? You could use something like -3, -2, -1, 0, 1, 2. And if you want to go the whole 9 yards, 3 to get some nice symmetry going. And systematically calculate by hand, or use Excel, which is probably more likely, to figure out what your outputs would be. What does that mean? It means you would take, again, the rule portion of this, and you would insert -3 here, -2 here, -1 here, 0. Some are easier than others. And then see what the output would be. So for example, I'll just put a half x, 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 and a half x. You get some kind of satisfaction when you do this by hand. So if I first start with putting a -3 in here. Remember, when you have an exponent raised to a fraction, you have to apply it to both the top and the bottom, according to rules for exponents. The effect of having a negative is that it will reverse things. You will have a 2 on top and a 1 on the bottom, and it will be cubed and cubed, like so. That means realistically that this is going to be 8/1, which is just 8. Again, a negative, as part of rules of exponents, reverses the position essentially of these two things. So what was on the bottom becomes on the top, and what was on the top becomes the bottom. Then it's just a regular 3, positive 3. 2 cubed is 8, and together you would have this as a ordered path, 3, 8. -2, same thing. If you apply it to a fraction, it affects both the top and the bottom, which is essentially this consequence. These reverse position, and that's squared, and this is squared, which is 4/1, which is the same as 4, and therefore you have a dot at the location of -2, 4. -1, one more of these, applied to the top, applied to the bottom, produces 2/1 to the first, which is the same as 2/1, which is really just 2, and therefore at -1, 2, you have a dot. 0, super easy, right? When you apply that to anything, with the exception of 0 itself, really, you would end up with 1 to the 0 over 2 to the 0, which is 1/1, which is just 1. So you go through the point as to be expected of 0, 1. If you have this to the first, that's not changing anything. That's 1 to the 1, 2 to the 1, which is just 1/2. So 1, half. And 2 applied to the top and to the bottom is 1 squared over 2 squared, which is 1/4, which is 2 to the quarter. And one more of these, if you cube something, a fraction in this case, top and bottom applied, 1 cubed over 2 cubed, you end up with 1/8, right? Notice instead of 8/1, it's 1/8. Instead of 4, it's 1/4. Instead of 2, it's 1/2. And then you have this 3, 1/8. Now, why bother with this? I think it gives a student more of a literal feeling, right, of what this involves if you actually do the brute force calculation even one time, right? You get the satisfaction of seeing a drawing, right? You have produced brute force literal ordered pairs, dots on a graph. So if you took this information and you graphed it on a coordinate plane, you could take this and now get the satisfaction of fleshing out a picture. I unfortunately did not strategically put that in the right place, but here I'll use a red and I'll move this if I have to. -3 along x is 1, 2, 3. Positive 8 would be 1, 2, 3, 4, 5, 6, 7, 8. You'd have a dot here. -2 back at the origin is 1, 2. Up 4 is halfway. 1, 2, 3, 4. Halfway. -1 from the origin is -1. Up 2 is halfway. And these 3 have been accounted for at this point. Okay. Now the next one. 0 is neither left nor right. Stay put for the horizontal. And up 1 would be half of 2. Over 1 positive, and then a half would be just approximately half that much, right? Over 2 would be half of the half, which is a quarter, which would be about that much. Over 3, a half of a half of a half is an eighth, so you'd have something that is, as you can see, very severely curving downward. All right. The thing is, it's getting closer and closer to y equals 0, but never reaches it. How come? Because you could keep chopping a half into infinity, right? Anyhow, that is very obviously a decay, right? There wasn't a negative involved in this, all right? It's just because we chose a base number that was a half, right? So it's shrinking like that. That's pretty cool, isn't it? I think so. All right, let me stop here. We're at 2 hours. And we're basically finished, all right, with chapter 6 and for the week. Okay, so for homework, if you're keeping pace, all right, for homework in my lab, work on section 610 and your rule square away. Okay, thank you guys for listening. I'll see you again on Monday. Careful out there.